All right, everybody. So this will be our first video that I guess you could say is actually calculus this semester. I just made a review video for a few things from algebra, but starting now, this is calculus. And the first topic that we study in calculus is that of a limit, okay? So in this video and in our first assignment, and probably for the first four assignments probably we'll see limits, these things called limits, in various forms. Okay, now just to get started, before we actually talk about what a limit is, in my last video I used a function kind of like this. Okay, and so let's just say that you have this function and you want to calculate f of 0. That's how you would read this function notation. And all that means is that if I take that function, whoops, oh my goodness. Hold on just a second. Okay. So this time, let's do like this. So if I take that function and I let the x be 0, then what happens as a result? Okay. Well, let's try it. So I would have to maybe get my handheld calculator. Okay, and I would have to do e to the power 7 times 0 take away 1 over 7 times 0, and then that would end up getting me 0 on top divided by 0 on the bottom, and that would be undefined. So that'd be my final answer about that. Okay, if you ask me to evaluate f of 0 for this function, if you ask me to let 0 be the input or the x, there is no answer that comes out of that, and it is therefore undefined. Okay, so let's just start there. For this function, you can't plug 0 in. That's just what it says. Now, that doesn't mean that something predictable doesn't happen if you're near 0, okay? So in calculus, like, we're often concerned with like very, very small changes or fluctuations, okay? That we don't just want to plug a number in and see what happens, from there, or what you get back out. We want to see like larger patterns and trends and things like that. So what I'm thinking with this function right here, that what we just saw is you can't plug in x is equal to 0, but something does happen, something predictable does happen if the x is close to 0. So for this function, I said, well, what happens if you plug in 0.01? That's not 0, but it's pretty close to 0. So here I did all the math, and with my calculator. Okay, so you'll need a calculator to do this. You might not have one like me, but you'll need a calculator of some kind. So I did that. I got 1.03. Okay, and then here I plugged in another number that is not 0, but is very close to 0. Okay, so negative 0.002. That's not 0. Very, very close. Okay, and oh, whoops, there's a kind of a typo right there. That number is supposed to be negative 0.002. Okay, so plug in that. It looks this way, right? And I get 0.99. So I think like something predictable does happen. Okay, it looks like even though you can't plug in x is equal to 0, the predictable thing that seems to happen if the x you plug in is close to 0 is that you'll get something out, you'll get some kind of result that is close to 1. Okay, you might not get 1, but it looks like you're going to get something close to 1. So that's a pattern that I want you to grasp as we're getting started here. Okay, so some number might not be allowed. It might not be within play or something like that, but numbers close to it might work, and then something predictable happens as a result. Okay, all right. So yeah, we might even wonder further, if we kept this pattern up, if I plugged in more and more numbers, could I support that or verify that pattern? that if x is close to 0, the y, the output, will be close to 1. Okay, so that's the question, or the trend, or whatever you want to call it. Okay, so if you're okay with that, then we can move on to the next thing. Now, that idea, that trend, that pattern I just asked you to comprehend gives rise to what a limit is. Okay, so this is the way that we write down the concept of a limit. Now, the way I would read this is I would say the limit as x approaches 0. Do you see that arrow? Gives the sensation or the impression of movement or direction. So we read that as the limit as x approaches 0. X arrow 0. Okay? Now notice that doesn't say x equals 0, because as we just talked about with this function, 0 is no good. Okay? So that's not an equal sign. It says x arrow 0, red, x approaches 0. All right, so we might say the limit as x approaches 0 for the function e to the power 7x minus 1 over 7x, or whatever that function is. Okay, so that's how you read it. Now, how you think about that as far as its meaning is that if x is very close to, but not equal to 0, from either side, what will happen? Okay, so 0 is no good for this function, but if the x is very, very, very close to 0 on either side of it, will there be some kind of predictability about what happens? All right, that's how you think of a limit. Now, let's go try out a problem taking that to its fullest extent. Okay, all right, so I gave you the meaning up here for what a limit is. Okay, so if I go to this problem and I say, okay, now it turns out there are lots of ways that you could calculate limits. And I won't discuss all of them in this video. But I'll show you the probably easiest way to get started, in my opinion. Okay, the instructions for like the first types of problems that you might see might be something along the lines of use a calculator to estimate the limit. They might say use a table to estimate the limit, something along those lines. So here's our problem. It says, what is the limit as x approaches 0 for the function e to the 5x minus 1 over x? Now, based on what I just told you up there, it says, what happens as x is very close to but not equal to 0 on either side? Okay, so like 0, if you look at the number line, there's 0, and then there's numbers on the right of 0, and then there's numbers on the left. Okay, so when I'm up here, and I told you the meaning of the limit, where was it? Yeah, if x is very close to but not equal to 0 from either side, what will happen? Yeah, so from either side, I mean left and right. Okay, so one way to figure that out is to use a calculator and make a table. All right, so like I mean, it's a lot of work the way I've done it for you in this video, but you know, here's my calculator, which I keep showing you, and I made this table. So you see these x's right here? What do all these x's have in common? Well, they're all very close to 0. I mean, very close. You might say the number 2 is close to 0. Or you might say the number 1.2 is close to 0. But that's not what I'm talking about. In limits, right here, when we say x goes to 0, and when we're trying to imagine what happens when x is close to 0, by close we mean very, very close. So we're talking decimals, like negative 0.08, negative 0.34, negative 0.004, okay? Now notice on my table, I have some numbers that are left of 0, and I have some numbers that are on the right of 0. Okay, like both sides. Okay, and then they're all like, notice again that the limit symbol is an arrow. It gives you the sense of direction. That these numbers are getting closer and closer and closer to 0. Closer and closer and closer to 0. That's why we use the arrow notation for limits. So it's like, here we're going closer to 0 that way, and then these numbers are going closer to 0, like meeting in the middle, okay? Now anyway, so that's what x goes to 0 looks like. To get the y's out of this function, I just have to do the calculation. How does a function work? You put a number in, you get a number back out. In this case, you put x in, you get y back out. Okay, so let's see. With my calculator, if I put in negative 0.08, I get 4.12. If I put in negative 0.034, I get 4.5, and so on. These are the numbers. Now, what pattern do you see? Look at that. Do you see a pattern to those? Do you see a trend? And what do you think? What are we after? If x is very close to but not equal to 0 from either side, what will happen? Well, it looks like the closer that the x gets to 0, the closer that the y gets to 5. That's what I'm seeing on the table. It goes from 4.1 to 4.5 to 4.99. And on the other side, as the x gets close to 0, 5.1, then 5.01, then 5.002, or 0002. So we would say this, that the answer to this question is 5. If the x gets closer to 0, you will find the y gets closer to 5. That's what we see in the table, okay? So summarize right here. All right, so that's one way that we can answer limits, is we can make tables, we can do the calculations and see the pattern or trend in the table. Few quick notes that limits involve numbers on a microscopic scale with lots of decimal places, okay? So remember on that other problem that I was talking about, I said like, well, you might think 1 or 2 or 1.3 is close to 0, but this is what we mean by x being close to 0 or x going to 0. Second thing, this number, did it have to be negative 0.08? And did this one that's a little bit closer have to be negative 0.034? No, I mean, the idea is that these numbers are extremely close to this one. Okay, extremely close to that one. But what they are doesn't make much of a difference. Okay, so whether that's a 4 or a 3 or a 1, doesn't really matter that much. And whether this is an 8 or a 7 or a 1 doesn't matter that much. Okay, you're going to see the same basic pattern. All right, so let's look at one last question then. So let's say the instructions are the same here, and it says use a calculator to estimate the limit. Okay, and this time the limit is the limit as x approaches negative 3. So how do we go about this? It's asking us, in this function, what happens if you let the x's get closer and closer and closer to negative 3? We're going to plug those numbers into this function, see what happens with the results, see if there's any kind of trend. So I made a table already, but I'm asking, like, over here, is there a pattern among those numbers? Is there some kind of trend among those numbers? Okay, this is the x's approaching negative 3. So remember, I put numbers closer and closer and closer to negative 3 from both sides. Very close, very, very close. Lots of decimal places close, you could think, okay? All right, now again, like we might think that, is negative 4 close to negative 3? Yes, I guess you could say it is, or some people might say it is, but that's not what we want when we're talking about limits, okay? So this is what x approaches negative 3 looks like. They might look like negative 3.1, negative 3.01, negative 3.001. Those numbers are what? These numbers are to the left of negative 3, and then on the other side I got negative 2.9, negative 2.99, negative 2.999. Okay, those numbers are to the right. Okay, so I got both sides, all limits consider both sides of the number in question. Okay, now again, I said it before, but we're all learning here, so I'm going to say it again. Does that have to be negative 3.1? Could it have been negative 3.3? Yes. Does this number, does that have to be negative 3.01? Could it have been negative 3.04? It doesn't really matter, as long as these get closer and closer to negative 3. Okay, now let's see. I did my calculations, and I got these numbers over here. For example, when you plug in negative 3.001, you get out of that function right there, negative 96.005, okay? But the overall pattern I see here is that the closer the x is to negative 3, the closer the y is to, looks like 96. Like here, we're running up against negative 96.005. That's really close to negative 96. And here we got negative 95.99. That is also really close to negative 96, okay? It looks like the closer these squeeze into negative 3, the closer that answer is going to squeeze in to negative 96. What if you're not sure? Well, you could always bump this up a little closer. What would make a number a little closer to negative 3 than that one? Put another 0 in. Try it out. Take that number, plug it into this function. I guarantee you'll get something even closer than what you see here, to negative 96. Okay, so there's our answer for this limit. So negative 96, okay. So we might say, as a formality, if we were going to read the answer or something like that, the limit as x approaches negative 3 for this function is negative 96. And you could think of it as x. Remember, limit notation has the arrows. If the x goes towards negative 3 microscopically on a very tiny scale with many decimals, you will find that the y goes to negative 96. Okay. Now, tables with a calculator is one way to do a limit. It's not the only way. So I'll be making other videos to show you other ways to do limits, but let me give a little preview of one right now. So see this function, let's see, yeah, okay, so x to the 4th power minus 2x squared minus 63 divided by x plus 3, okay? When I say this, when I say if the x is close to negative 3, what will happen is the y will be close to negative 96. We could also see that on a graph if we had the ability to generate that graph. And now these days it's pretty easy to do that, all right? So if you don't have a graphing calculator, that's okay. Well, there's an online graphing calculator that I notice a lot of students use at Desmos, okay? So here I entered this function in Desmos to draw the graph, okay? And if I was going to answer this question, this limit by this graph, I have to see, well, what is the y doing when the x is close to negative 3? I would have to figure out that information from the graph, okay? So it's drawn the graph for me, so it's like I don't have to think about that. But it's such a weird looking graph that I don't know, like, where's negative 3? Negative 3 is right here for x. Do you see that? And like the rest of the graph doesn't even show up. So I could either zoom out or something like that, or try to like go over to that part of the graph. But nonetheless, let's see if we can do it. All right, so I want to see what happens on this graph when the x is near negative 3. So I guess I'll zoom in about this close. So there's 20, so that means this is 5, and negative 3 would be about right there. And then I have to go down to like right about here, or about there. And it's hard to tell exactly from the graph, because the graph, at least as I see it right here, is not that precise. But what does that number appear to be? It appears to be like it might be in the mid-90s or so. And what did we find out? See, the same thing right here. We said, well, if the x is close to negative 3, you'll get a y somewhere in the vicinity of negative 96, okay? Yeah, I mean, that's I can, I might not have judged it to be exactly negative 96 from this graph, but it does support what I just did on paper. And perhaps you could see that if in some future videos we do some of the graphs or some of the limits by just graphs, okay? So long as you can see the graph in enough detail and generate it correctly right in front of you, then yeah, we might be able to tell the same thing. The graph is the same information. Every single point on this graph is just an X and a Y, okay? So in fact, like here, I'm tracing it. That point right there is a point that could have been on our table. Negative 2.95 for X, negative 93.43 for Y. And negative 2.96 for X, 93 negative for Y. Let's see how close we can get. Negative 2.99 for X, negative 95.481. So yeah, that's the graph and the table is really the same thing. All right. So yes, we will be doing tables sometimes. We will be doing graphs sometimes. But it's all the same concept and it's the same information either way.